Liftoff! Liftoff of Falcon Heavy with Europa Clipper, unveiling the mysteries of an enormous ocean lurking beneath the icy crust of Jupiter's moon, Europa.
Side booster separation confirmed.
Fairing is separated, and those will be recovered by SpaceX's own recovery ship, Go Cosmos.
This is a big moment for the program, for NASA, APL, and JPL. Let's watch.
Europa Clipper, separation confirmed.
And there you go. NASA's Europa Clipper probe, embarking on a long-awaited mission to study Jupiter's icy moon, Europa. And what a sight.
Jupiter, the largest planet in our solar system, the fifth planet out. This is all the planets in our solar system to scale in size, but not distance. It's actually about 5 times as far from the sun as the Earth is. And back in the 1600s, when Galileo Galilei looked at Jupiter with his telescope, which probably many of you in this room have done, hopefully with better telescopes than he had, it was not just the resolved disk of the planet that fascinated him, but it was also these 4 dots of light that he saw around Jupiter. And they moved on kind of an hour to daily time scale. And that observation was really the key to the whole Copernican revolution that kind of changed our whole view of where we are in the universe. Things don't all revolve around us. These satellites are actually orbiting another planet, and that was huge at the time. Even though they were just points of light, that really changed everything that we thought about our solar system. Since then, we've been very lucky to visit the Jupiter system with a handful of different missions. Starting with Voyager in the 70s, the Galileo spacecraft spent a long time there around the turn of the century. Most recently, the Juno spacecraft has visited and given us brand new data. And these points of light have really become whole worlds in our view. So no longer are they just a little dot that's moving around, but they're whole globes each with their own unique geology and history. You've probably heard of the closest one in, Io. It's the most volcanically active body in the solar system. I'm going to be talking about Europa, which is the second moon out. Ganymede and Callisto are also really interesting in their own right. These icy, rocky bodies covered with craters that we think are quite old. So what we do know from all these previous visits to Europa is kind of a qualitative understanding of the interior structure of this moon. We know it has a water ice crust on the outside. It's frozen because it's very cold out there. But it also has a liquid ocean of water underneath that ice crust. And below that, it has a rocky mantle and probably a metallic core, much like the Earth. So how do we know there's an ocean when we really haven't visited it? It's covered with this frozen crust. We can't sample down there. The way we can tell, the strongest evidence for this, is from the magnetic field. So Jupiter has this really, really strong magnetic field. It's 20,000 times stronger than the Earth's magnetic field, which we use all the time with compasses and GPS. And that really strong magnetic field actually induces a separate magnetic field in Europa as Europa passes through the field lines of Jupiter. So the Galileo spacecraft was able to measure the strength and orientation of that magnetic field and see that it was changing with the orbit. And how do you induce a magnetic field in a body like this? There has to be some sort of flowing conductor, some sort of conducting liquid. And the best explanation for something like that is a salty ocean. So we know that there's a salty ocean under there. We don't necessarily know how thick it is, but we know it's there, we know it's global. Now, how do you maintain this much liquid water out at the Jupiter system? It's very cold out there. It's 5 times further away from the sun as the Earth is. It's so cold that the outer shell is completely frozen. There's never any melting of that water ice. But the unique configuration of this system allows this ocean to have formed and to have persisted for billions of years. So on the left, you'll see an animation that's exaggerated. These are both exaggerated. As Europa moves around on a slightly elliptical orbit, it's actually stretched on this tidally locked orbit so that as it moves closer and further away, that tidal force on it actually changes on a 3.5-day cycle. From the perspective of Europa itself, it's getting constantly squished. Again, this is an exaggeration. It's just a little bit of squishing, but it's enough to cause friction in that rocky interior, and that frictional heating is enough to maintain this ocean over billions of years. So not only is there a lot of water there, we think there's probably even more than there is on the Earth. If you take all of the Earth's oceans and you added them together, the amount of water on Europa is maybe as much as twice that. This is one of the questions we want to answer, exactly how much water is there. But there are a lot of similarities between Earth and Europa that you might not have expected. Europa is much smaller. It's about the size of our own moon, a little bit smaller than that. But it has maybe twice as much water in the form of a liquid saltwater ocean beneath the surface. The structure, we know there's an ice crust at the surface over that liquid ocean in contact with a rocky seafloor, much like on the Earth. And why are we so concerned with water? Well, everywhere that we find water on the Earth, we find life. So this is probably one of the best places in the solar system to look for life other than the Earth. The result of that structure with the icy crust over the liquid water ocean is that it has some really unique geology that we don't see anywhere else in the solar system. So it's got this really fascinating surface. Even though it's very, very smooth at the large scale, there are a lot of variations when you zoom in up close. It's kind of got this like ball of string appearance, you might notice, and that is caused by these long, long ridges, cracks that have parallel ridges on either side, maybe something like a spreading center. These are thousands of kilometers long. They can be straight to slightly curving, and they're overlapping, so we can see generations of these having formed. There are a few craters, even though this is a fairly smooth, fairly young surface, geologically young surface. There are a few impact craters. This is an impact crater named Puil, and it has kicked up fresh material that has not been radiation processed like everything else on the surface. That's what these really bright rays of ejecta are. There are things called lenticulae, which basically just means spots, because we don't really know what they are. Some of them are domed upward, some of them are pits, and some of them actually have compositional differences. If you can see, some of them look darker in this stretched image. So it might be that these involve some sort of liquid water interacting with the surface and transporting materials. There's some areas of terrain that is just all jumbled up and messed up and confused, and so scientists creatively called it chaos terrain. This looks like the pre-existing surface has broken up. These blocks have moved around, they've rotated, they've tilted, and then been frozen back together by this fine-grained matrix. And you can see too, when we stretch these images to get out the color differences, you can see that there are some really interesting materials here. So we think that these might be some of the freshest and youngest surfaces on Europa. This is a specific chaos terrain called Connemara chaos. And you can see these blocks that have been broken apart and tilted. You can see some of these ridges that are pre-existing and some that came after. So we can kind of piece together these geologic histories where we have data that's good enough, which is not too many places yet. This is an artist's conception of one hypothesis for how chaos terrain forms. If there is heat coming from below, it's possible that that icy shell is actually partially molten or maybe just made of like squishy ice. And you could actually get convection within that ice shell, bringing heat up from the bottom that could then melt part of that ice. And you could end up with a kind of a stranded pond of brine beneath the surface. And maybe that kind of pokes through and allows these chaos terrains to form where the blocks break apart and fall in. So this is really interesting because if liquid water is that close to the surface, we really want to see what's in there. This could represent one of the habitable environments that we're really searching for, that we would be excited to find. So this is kind of a cross-section of Europa's crust. With some of the processes we think might be going on. You could have warmer flowing ice, moving heat and materials and nutrients around, and the upper layer cold, stiff ice is occasionally penetrated by either these warm pockets or maybe by cracks that allow material to flow upward, maybe even from the ocean itself to the surface. And this is a really, really exciting, if it's true, it's really exciting to think about this warm, briny ocean water mixing with radiation processed organics that are deposited on the surface, and what that means for the chemistry and the habitability is really exciting.